Hi, I am Ankit and welcome to Trabotech. In this video, we will learn what are different assumptions an explainer use in GNN. So first of all, we will have a recap of what is the objective of an explainer, and then we will come to what are assumptions and what is their need. Right? And then one by one, we will discuss assumptions like mean field assumption, soft importance scores, explanation lies close to the target node, and smaller the subgraph, the better. Now, there is no hard and fast rule that an explainer tool should use these assumptions or not. It basically depends upon the objective or the idea behind the explainer tool. So, it may be possible that an explainer is basically using more assumptions than listed here, or it may be possible that an explainer is not using some of these assumptions. So this is all relative, but these are some of the common assumptions that are being used already in the explainer tools that we have. So the objective of an explainer is basically to identify important substructures within the graph. Uh, for example, if we talk about GNN explainer as an explainer tool, then it identifies important subgraphs and important node features within the graph. So these are the substructures here. And by important, we mean that these substructures are basically influencing the model predictions. Now, what does that mean? That means if we are inputting complete graph in the GNN model, so the model will make some prediction, right? Now, when we input these important substructures like subgraphs or node features into the GNN model and not complete graph, then also the predictions are closer to the original prediction. So this basically signifies that the structures that we are entering into the model are significant or they are important, right? They are influencing the model's predictions. They have a say in the model's predictions. Their contribution is high in the model's predictions, right? For example, if we have a molecular graph like this, so this functional group could be one important subgraph in this whole graph, right? Now, a graph can have thousands of nodes. For example, if we are talking about a social network, right? If we are talking about bank accounts, for example, or if we are talking about diverse molecules in chemistry, right? So a graph can have thousands of nodes. And if we have thousands of nodes, the number of possible subgraphs is also very large, right? So the problem before explainers in this case is trying every possible subgraph to check whether it is important or not by inputting it in the GNN model and checking the influence on predictions is actually not computationally possible. So explainer basically makes assumptions to ease this process. So these are basically you can think of as shortlisting criteria, right? That makes the process computationally more efficient. So one of the assumptions that an explainer can use is mean field assumption. Now, what does it say? It says that each edge has its own level of importance, which is independent of other edges. So, what normally used to happen while identifying, for example, different important subgraphs within a graph, an explainer is basically looking for combination of edges, right, for subgraph. Now, with this assumption, instead of saying or instead of finding combination of edges that matters, we are basically saying that each edge contributes some amount to the prediction. Now, for example, in this graph, you can see that edges have independent importance score, and this is also applicable to other edges for which they are not shown. So now how this assumption basically helps. So the model doesn't have to test every edge combination here, right? So this reduces a lot of computational complexity for the experiment. Now, just like edges for identifying different important subgraphs, this mean field assumption is also valid for node features. Node features also can have their own importance score. So instead of testing every feature combination, we can learn which feature matter more and which ones can be ignored. Another assumption which an explainer can use is soft importance scores. Now, what this means is that importance is gradual and not binary. So instead of the edges importance scores being 0 and 1 strictly, now they can have any real value between 0 and 1. So they are also called soft masks, right? So instead of saying here that this edge is important or this edge is useless, now what we are saying is that this edge is very important. This edge is somewhat important. This edge barely matters, right? So, for example, uh, an edge score between zero point 0.5 and 1 is now different from an edge score between 0 and 0.5. So how this assumption helps is that it allows a smooth learning using gradients. So with soft scores, where the scores can vary between 0 and 1, we can compute gradients, and this basically allows a smooth learning and easier optimization for the explainer, which is not possible in the case of discrete values where the edges score are only 0 and 1 strictly. Right? This also avoids combinatorial explosion. Now, what this is, we will see on the next slide. But before going to the next slide, I want to tell you one downside of this assumption. So while this assumption is making the process computationally efficient, there is always the cost of anything, right? So the downside here is, for example, the soft mask value comes zero point 0.7. So the edge is basically zero point 0.7 times important. Now, what does that mean structurally? It means nothing, right? So while the soft importance scores are mathematically meaningful, they are semantically meaningless, right? The edge can either be present or it can be absent in a graph. There is nothing like zero point 0.7 edge, right? So this is the downside of soft importance scores, and they are therefore not preferred usually in the case of edges. And some of the explainer tools prefer using soft importance score, whereas others use different techniques, which we will see in other videos. So what is combinatorial explosion, right? For example, you have 20 edges in your graph. So with 20 edges, if we have 0 and 1, strict 0 and 1 as important scores, then there are over 1 million possible combinations of subgraphs, right? And the mathematics is shown here, 1048576, right? That's more than a million. Now, when we have 50 edges in a graph, this number crosses a quadrillion. Right, so this is insane. This is insane for the explainer to compute, basically. Now, what we are doing in assumption 1 and 2 together is that we are changing this problem. So instead of computing which combination of edges is correct, we are now computing how important is each edge. And that reduces a lot of computational load on the explainer. Right? Another assumption that an explainer can use is explanation lies close to the target node. Now, what this means is that the most important information comes from the local neighborhood of the prediction target. and not from the distant nodes, right? So distant nodes are less likely to matter. Now, this assumption basically aligns the way with GNNs actually work, right? So you know already that in GNNs, information flows layer by layer. The information which is only a few hops away influence more compared to the information which is farther away, right? So this assumption basically helps the explainer by not focusing on the entire massive graph, right? And to only focus on the computation graph, right? Only in the local neighborhood. So this also reduces a lot of computational load on the explainer, right? Now the downside of this assumption is if you know about GNNs, then you may be knowing one term called expressive power, right? How much expressive a GNN is. So by focusing on the local neighborhood only, the explainer becomes less expressive, right? So this is the cost of increasing computational efficiency. Now, computation graph could be a new term for some of you. So a computation graph basically looks like this. If we have a graph like this, so for node 1 is basically connected to node 2 and node 3, right? And then node 2 is connected to 1 and 3, like this. And then node 3 is connected to 1, 2, 4, and 5, like this, right? So the information from 1, 2, 4, and 5 basically flows into 3, from 1 and 3 flows into 2, and then the information from nodes 2 and 3 basically flows into 1. So this is a three-layer computation graph. This is layer 1, this is layer 2, and this is layer 3, right? So if, for example, a GNN has three layers like this, so the computation graph looks like this, and that means that a node only receives information from neighbors up to 3 hops away. So the computation graph here includes the target node, its neighbors, their neighbors, and the edges connecting them. And everything that falls outside this region never affects the prediction. So this is the assumption of the experiment, that it only looks into the local neighborhood via the computation graph, right? Another assumption that an explainer can use is smaller the subgraph, the better, right? So the compact explanation is basically preferred than a larger explanation. For example, if the graph looks like this and these are the possible subgraphs, then this particular explanation, which is smaller, is preferred compared to the larger ones. So the explainer prefers fewer nodes, fewer edges, and simpler structures, right? And this is implemented using regularization, which basically is penalizing explanations that are too big or messy. Now, what this assumption basically does, it improves interpretability of the model, right? So now the prediction of the GNN model can be explained by a smaller entity. So that means that this entity contains more dense information compared to the other subgraphs which are larger, right? So the smaller the subgraph is, the more dense meaning or more dense information it basically contributes to, right? So this is the benefit of this assumption. Also, this assumption avoids trivial explanations like, for example, whole graph is important because the whole graph always gives you the same prediction which the whole graph gives itself, right? So these trivial explanations are also avoided by using this assumption, right? So this is it in this video. So we first discussed what are assumptions in explainer and why are they required, and then we discussed different assumptions like mean field assumption, soft importance scores, explanation lies close to the target node and the smaller the subgraph, the better. We looked at the pros and cons of each of the explainers. So I hope you now have a good understanding of how different assumptions basically work in explainers. So if you have any questions, feel free to leave comments. Thank you so much for watching. Wish you all the best.